In this video, we're going to look at balancing chemical reaction equations. Now, the first question you might be asking is, why do we even care? Why do we even need to do this? Well, the reason why is because we want our chemical reaction equations, we want this right here, this is a chemical reaction equation, we want that to represent the law of conservation of mass. Now, the law of conservation of mass tells us that before and after any sort of change happens, mass has to stay the same. So our total number of particles of each type of atom needs to stay the same, even if they're bonded in different ways. So we need our chemical reaction equation to show this. So our Y is the law of conservation of mass. And this is going to become even more important later when we start to do math and calculations with this, because those coefficients that we're going to add when we balance these chemical reaction equations are going to become super important. So before we jump into actually balancing, let's look at kind of the anatomy of a chemical reaction equation. So you're always going to have something on the left, something on the right, and an arrow in between. So what you're starting with, what's on the left side of your arrow, is those are your reactants. Those are your starting materials. What's on the right side of your arrow, those are your products. Those are what you're making at the end. Now, a lot of this we already know. We know chemical formulas. We know what the subscripts mean. There might even be in some of them a state of matter, so a parentheses with a letter. So our states of matter are solid, liquid, and gas. So if you see a parentheses with either an S, an L, or a G, that's telling you the state of matter. What's new when we balance, and this is what the only thing we're going to be changing when we balance a chemical reaction equation, are these big numbers right here. Those are the coefficients. And our coefficients tell us two different things. Our coefficients tell us the number of moles of each type of particle, and our coefficients tell us the number of particles. So since we're going to be drawing particle diagrams and thinking of this right now on a particle level scale, these coefficients are going to tell us how many particles of each type. So when we go to balance a chemical reaction equation, the only thing that we are ever allowed to change are the coefficients. You can't change the subscripts, you can't change the chemical formulas, you can't add any more additional formulas. The only thing you can change are your coefficients. So those are the constraints that we're going to work in. And we're going to start just by looking at an already balanced chemical reaction equation, and we're going to draw a particle diagram for it, just so that we can help visualize this a little bit more. So before I can draw my particle diagram, I need to assign some symbols. So I'm going to make my phosphoruses triangles, and I'm going to make my oxygens circles. So this reaction equation tells me that my reactants, I have one P4, so P4 is going to be 4 triangles stuck together. And then I have 3 O2s. So an O2 looks like 2 circles stuck together, and I have 3 of them, because that's what my coefficient tells me. In my product side, I have only one compound. I have P2O3, and I have 2 of them. So one P2O3 would be 2 triangles and 3 circles, and I have 2 of them, so I need another one. So 2 triangles and 3 circles. Now, if I wanted to check the law of conservation of mass, I'm going to check to make sure that I have the same number of triangles and the same number of circles before and after. So I have 1, 2, 3, 4 triangles. I have 1, 2, 3, 4 triangles. So that's good. And then I'm going to check my oxygens. I have 6 over here. 1, 2, 3, 4, 5, 6. So I should have 6 after. 1, 2, 3, 4, 5, 6. So that helps us visualize by drawing this particle diagram. It helps us see how our total number is staying the same, even though they're being bonded a little bit differently. So let's look at a different type of example. So in this one, the particle diagram is already drawn for you. And then the reaction down here has blanks. It does not have any coefficients. So we're going to balance this based off of our particle diagram. So our H's are squares, nitrogens are triangles, O's are circles. So this looks like we only have one type of compound, which matches down here. We have an HNO3, so there's our HNO3. since we have 2 of them, I'm going to put a 2 in front. And then over here, I have 2 products. I have an N2O5 and I have an H2O, and I only have 1 of each. So I'm going to go ahead and put 1s there. And just to double check and make sure that I didn't make any mistakes when I drew the particle diagram to start with, I'm going to check to make sure that I have the same number of squares and triangles and circles before and after. So I have 2 squares, I have 2 squares, I have 2 triangles, I have 2 triangles, and I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 circles. So I'm good. Now I want to make a note here. On the previous example, the P4 didn't have a number in front of it. So similarly, when we write chemical formulas, like here, if we just have the element symbol but no subscript, it's assumed that it's a 1, and we don't have to write the 1s there. Same goes with the coefficients. We don't have to write a 1. So if you were to see this reaction equation already balanced, what you'd see is 2HNO3 goes to N2O5 plus H2O. It's helpful for our purposes, though, if we're filling in the blanks, to put the 1s, just to make sure that we know that we didn't accidentally forget to put something there. But you don't have to put the 1s as coefficients when you're writing balanced chemical reaction equations. So this is all well and good with particle diagrams, but do we really want to draw particle diagrams every single time we want to balance chemical reaction equation? Hopefully you're saying no, because that would be a huge waste of time. It's good to start with, and it's good especially if you're an extremely visual person. It's a good way to help you kind of visualize what's going on, but in reality it gets kind of tedious, and we don't really want to have to do that every single time. So let's look at 2 examples where we're going to balance without drawing particle diagrams, and I'm going to walk you through my thought process. Okay, example 1, ignore the bottom one for right now. Example 1, sodium plus chlorine produces sodium chloride. So we have an Na and we have Cl2 producing NaCl. So normally when I go to balance chemical reaction equations, I do everything except hydrogen and oxygen. I leave hydrogen and oxygen for the end. Why? Well, when we look at more complex reaction equations, oftentimes hydrogen and oxygen can show up in several different compounds in both the reactants and the products. So it makes it hard to start with those. Oftentimes, if you start with the other elements in the reaction equation, the hydrogens and oxygens will kind of sort themselves out by the end. This one, however, we don't have any hydrogens or oxygens, so we kind of just have to pick one. Doesn't really matter. So I'm going to work from left to right. So right now I have 1 sodium in my reactant and I have 1 sodium in my product. Are those balanced? Are they equal? Yeah, 1 equals 1. Okay, so let's move across. Let's look at my chlorines. I have 2 chlorines in my reactants and 1 chlorine in my products. Are those balanced? No, they're not. So I have 2 here, I have 1 here, so I'm going to add a 2 in front, because this 2 distributes to everything inside that reaction equation. Now, I cannot add my 2 down here. That totally changes the chemical formula, so I can't do that. Remember, the only thing you're allowed to do are to change the coefficients. So now I have 2 chlorines and I have 2 chlorines, but what else did that change? Change the sodiums as well. So now I have 2 sodiums on my products. I only have 1 on my reactants. So that's a pretty easy fix. I just add a 2 right there. So just to fill in the blanks, remember you don't have to include the 1s. I'm going to go ahead and put a 1 here. So if we were writing this without filling in the blanks, we would write this as 2 sodiums reacts with chlorine gas to produce 2 sodium chlorides. And that's what that would look like when it's balanced. That one was pretty easy. Let's try one that's a little bit harder. So we have C4H10 reacting with oxygen gas, producing carbon dioxide and water. So this is a really good example for waiting to do the oxygens and the hydrogens, because while hydrogen only shows up in one thing in the reactants and one thing in the products, oxygen gets split. So we're going to start with other things first. So we have 3 elements. So my plan of attack is I'm going to do carbon, then I'm going to do hydrogen, and then I'm going to do my oxygens last. So let's do carbons first. I have 4 over here because I have C4. Over here, the only place of my carbon is in my CO2 and I have 1. So 4 does not equal 1. So I'm going to add a 4 in front over here. Okay, so now I'm going to look at my hydrogens. So I have 10 hydrogens in the reactants. I have 2 hydrogens in the products. 10 does not equal 2. However, if I put a 10 here, now how many hydrogens do I have in my products? I have 20. It's not really what I wanted. I only wanted 10. So I'm not going to put a 10 there. I'm going to put a 5. And I'm going to put that 5 because that 5 distributes. So 5 times 2 gets me 10. So you see how I did that? 5 times 2 gets me the 10 that I need. So you're not always going to put the number in front that you, the total number that you need. You got to take into account the subscripts. Okay, so we did carbons and we did hydrogens. That was pretty straightforward. Let's check my oxygens. Well, I have 2 over here. Let's add them up over here. I have 4 times 2, that gets me 8. I have 5 times 1, that gets me 5. 8 plus 5 gets me a total of 13 oxygens on that side. Okay, fair enough. Over here, if I put 13 in this blank, 13 times 2 gets me 26. That's not what I wanted. I wanted half of that. I wanted 13. Well, over here when we did that, we just cut this number in half. Can I cut 13 in half? No, that would get me a decimal. Do you think you can have decimals as coefficients? Well, it would make life a lot easier if we could, but actually we can't. Coefficients have to be whole numbers. So that's yet one more rule of balancing chemical reaction equations. You cannot have decimals or fractions. They have to be whole numbers. So I'm going to show you a little trick. If you end up in a spot where you can't come up with a whole number to fill this, here's a trick. Try doubling everything. So I'm going to make this a 2. I'm still going to leave this blank because we haven't figured out what number that's going to be yet. Instead of a 4, I'm going to turn this into an 8. And instead of a 5, I'm going to turn that into a 10. Okay, before I move on, let's just go double check our numbers. Let's check carbon. 2 times 4, that gets me 8. 8 times 1 gets me 8 carbons, so those are still good. 2 times 10 gets me 20. 10 times 2 gets me 20. So my hydrogens are still good. Okay, so now let's check our oxygens. Let's do this again. So 8 times 2 gets me 16. 10 times 1 gets me 10. 16 plus 10 gets me 26 oxygens. 26 divided by 2 gets me 13 oxygens, or 13 O2s, which gets me 26 total oxygen atoms. So if you ever get stuck and you can't come up with a coefficient that's not a fraction or a decimal, try doubling everything. See if that works. Oftentimes, that will solve the problem. Now, kind of the last thing about coefficients is that they need to be in the lowest ratios possible. So if you can go through and divide all of your coefficients by 2, divide all of your coefficients by 2. They need to be as reduced as possible. Kind of like fractions, you want to reduce them as much as you can. So if I look at this one, these numbers are kind of high. So let's just check and make sure. That I can divide by 2, that I can divide, my 8 I can divide by 2, my 10 I can divide by 2, my 13 I can't. So believe it or not, even though these are fairly high coefficients, this is actually the balanced chemical reaction equation. So be patient, take your time. Remember, they need to be whole numbers. You need to have the same number of each type of element on your reactants and your products. And when you're looking at a more complex equation, start with elements other than hydrogen and oxygen, then do hydrogen and save oxygen for the end.